Greetings. We will now do a little preview of Chapter 9. I'm going to do a problem that's actually the sort of thing you'll see in Chapter 9, Section 2, and it includes stuff from Chapter 9, Section 1, and Chapter 9, Section 2, because Chapter 9, Section 1 is basically also an introduction to a lot of the terminology which we're going to talk about here. So I'm going to go through this sort of quick, and we'll cover it certainly in more detail when we get to those sections. So this is just, in essence, a little preview. And so, this problem says this, and so it says McGill has claimed that 15% of the fruit gushers, 15% of fruit gushers are orange. He decides to test this. He takes a random sample of 400 fruit gushers and finds 80 of them are orange. Do the data provide statistically significant evidence that the portion of fruit gushers is greater than 15%? Perform a test of significance. And this is also known as a hypothesis test. And so the gist of what's going on here is we're going to test this claim. And in each of these problems, there's going to be some form of claim that we're going to test against. And in this case, it's 15%. And our sample data, our sample statistic, in this case, our p hat is equal to, we got 80 out of 400, and that is equal to 0.2 or 20%. And so it's certainly greater than 15%. But the big question we're asking, is it so much bigger than 15% that it would cause us to doubt this claim? And we did this very sort of problem in Chapter 7, but we're doing it sort of more in a formal way now. And so whenever you have to do a test of significance, we've got to write out a little mini essay. And the mini essay for testing, you remember for confidence intervals, it was TAME. It was TAME. Well, we're adding an H to that. It is THAME. Whenever you do a test, you have to do the THAME acronym. You have to do 5 things. The T, A, and the M, and the E are basically the same sort of thing. The type of inference, the assumptions, the mechanics, and the ending. Of course, the mechanics and the ending are going to be a bit different, and we'll talk about that when we get there. The H is where we have to write hypotheses. Whenever you're doing a hypothesis test or a test of significance, we have to write out hypotheses, and so that's going to take a little bit of practice. But so here we go. And so the T is the type of inference. And so the type of inference that we have here, the T is for the type of inference, and we are doing a one proportion z-test. Okay, and if you forget that name, it's on your calculator, and I'll show you that in a minute. So then this is going to be new for us. We have to write out some hypotheses. And so 2 of them. We got to write out what is known as a null hypothesis. Now, the null hypothesis, which we symbolize by H sub O, we put H sub O in a colon, and then we're going to put whatever's claimed. In this case, it is that P, the proportion of all fruit gushers that are orange, is equal to 0.15. So your null hypothesis is always going to be P is equal to something in essence, or mu is equal to something, or most of the time, most of the problems we're going to do. Or it could be, in section 9.3, it's going to be that a difference, about a difference in proportions. But anyway, so the null hypothesis is whatever's claimed in the problem. It's always going to be P is equal to something. In section 9.2, it's going to be P is equal to something, okay? So the alternative, which we write as H sub A, is what we are testing for or what we think might be true. And so in this case, it is, do we have evidence that gushers is greater than 15%? So that's what our alternative is. We're testing for greater than, like that. And so that's what your null and alternative hypotheses are always going to look like. This is always going to be equal to, this is always going to be either greater than, less than, or not equal to. And so we'll practice that. And then you have to define P. Anytime you write a variable, you need to define what it is. And P is equal to the proportion of all gushers that are orange. And so there we go. So that's how you do your hypotheses, okay? And so that's new for us. Now the A, the assumptions, is basically the same thing as last chapter. So in regards to our assumptions, in other words, our conditions is assumptions, otherwise known as our conditions, we're going to sin again. So same thing as last chapter, in essence, pretty much. All right, so we are going to sin, S-I-N. And so this, the S stands for SRS, or random. And so in this case, you notice it says random sample up there. So just like last chapter, we would say it says a random sample was taken, so random condition is met. And we're going to have this condition basically every problem the rest of the year. So you might as well get used to saying it. Okay. All right. So then we have independence. You know, this aspect of the word independence means our sample size must be less than or equal to 10% of our population size. And so because we aren't sampling with replacement, we are taking 400 fruit gushers out. And by doing that, we're changing the population of fruit gushers ever so slightly in this case. But because our population is so big, it's not changing it significantly. So what you would in essence do is you would say, well, if the sample size has to be less than 10% of the population size, that means there's got to be at least 4,000. Okay. You just multiply that times 10. And so you'd say this, there must be at least 4,000 gushers in the world for our little n to be less than or equal to 0.1 times our big N. Little n is the sample size, big N is the population size. That was just like last chapter as well. We have normality, which is very similar to last chapter. Remember last chapter, normality, n times p hat and n times 1 minus p hat are greater than or equal to 10. But we're not going to use p hat this chapter. That would not be right to do. We are using p naught. And you say, what is p naught? P naught is the hypothesized p. See, the whole premise of this test is we are going to use the logic of if we assume the null is true, what's the probability we're going to get a sample value as big or bigger than the sample value we got? Okay. And so we are assuming in essence, in a way that this null is true. Let's just assume that 15% is true. So we're going to use 15% for that. And so so this would be 400 times 0.15, and this would be 400 times 1 minus 0.15, which would be 0.85. And let's see what those are equal to. And so we would have 400 times 0.15. And so that's equal to 60. And then 400 times 0.85, and that's equal to 340. They're both greater than or equal to 10. So we would say thus normality is met. Thus normality is met. Right, like that. So that one's a very similar to what we had in the last chapter, but it's slightly different. And these other two are the exact same. So hopefully you're getting used to the assumption. That's the most involved part of it. Now we have our mechanics. Okay. So our mechanics for a test. Now, you know, when we did an interval, we would just make the interval here. But it's going to be a little bit, I think, a little bit more complicated here. All right. So we are going to find the p-value. So what you have to do is, in essence, find what is known as the test statistic. The test statistic, and that is z in this case, and the p-value, and that's the big number. And there's three ways of finding a p-value. And I want to do, first of all, I'm gonna just go ahead and show you one way that we did in chapter 7 in regards to a p-value. And so what we'll do is this, is if we assume that 15% is the true population, we're going to use the concept of a sampling distribution. What's the probability, see, that we are going to get a sample proportion as big as 20%, which is one we gotten, or bigger? And so, in other words, let's use a sampling distribution just like we did in chapter 7. Well, if 15% is true, our sampling distribution is going to look like this. In other words, every possible value of p hat, just as we, in repeated sampling, just as we talked about in chapter 7, if we took many, many different samples, if 15% was true, our p hats are going to be somewhere around p hat. And they're going to vary normally, approximately, because n times p and n times 1 minus p are greater than 10. And so, all right, so let's say this is all the possible values of p hats. What's the probability we're going to get that? Okay, we're going to get 0.2 in a sample of size 400. So 0.2 is somewhere over here to the right of it. So there's 0.2. So what's the probability? The p-value is the probability of that or more unusual. We go greater than because that's what the alternative says. If the alternative said greater than, you go greater than. If it had said less than, you go less than. And so how can we find that area? Just like what we did in chapter 7. We'll do normal CDF. So my lower bound is 0.2 of my shaded area. My upper bound is infinity. And this is 0.15. And then the formula, so let's go to our formula sheet for our standard deviation, you may recall, is going to be in essence, it is going to be, this guy right here, except we're going to use P naught in there. Okay, P naught. And so it is going to be the square root of 0.15 times 0.85 over 400. And so let's find that guy. And so we will say second VARS, which is distribution, normal CDF. And then we will enter in 0.2 to infinity, or like 9 billion would take care of it. And so this would be 0.15, and this would be the square root of 0.15 times 0.85 divided by 400, right like that. And so that would give us, and there's our p-value, 0.002551 approximately. And there we go. And so that is one way to find a p-value, okay, right there. Okay, now, so how do you find your test statistic, and what is your test statistic? And the test statistic, in essence, identifies what sort of test you're doing. We have lots of different kinds of tests and stats. We have z-tests, we have t-tests, we have chi-square tests, we have all of them. So you are expected to find the test statistic. And so our test statistic, and let me show you on your formula sheet, your standardized test statistic, it is in essence going to be a z-score. It is going to be your statistic minus your parameter over the standard error of the statistic. So our statistic is z. And so it's going to be z, okay? Now, that is our test statistic. And our sample statistic is p hat minus, in essence, our parameter. Well, our parameter is p, but we're assuming that it's 0.15, right? So it's going to be our p naught. So it's going to be our p naught over the square root of p naught times 1 minus p naught over n. And so, and then that formula is the formula for our, in essence, the formula for our standard error here, which we're using p naught as opposed to p hat. So it's just in essence that thing. And so when you enter in these numbers, so you would get, this is 0.2 minus 0.15 over the square root of 0.15 times 0.85 over 400, and that is equal to 2.80056. And it is in essence the relevant test statistic. It's the relevant z-score, just like very similar to what we found in chapter 2. So there's my test statistic right there. And so one other way that I'll show you quickly before we do our ending to find your p-value is you could do this. All right, you could do this. So we are going to hit the stat button, and we're going to go to tests, and we're going to go down to option 5. So in this chapter, we're using option 5 and option 6, a 1 proportion z-test and a 2 proportion z-test. And there's the name of the type of inference. If you forgot the name of the type of inference, there it is. So 1 proportion z-test. So our p naught, our hypothesized p in this case, is 0.15, like that. So, and then our x, our number of successes, that goes to our sample. So that'd be 80 out of 400. So that'd be 80 out of 400, right, like that. And then this line is what our alternative is. In this case, our alternative, since it asks for greater than in the problem, so we are going for greater than, and then you hit calculate, and it gives you your test statistic p-value. Those are the two numbers you have to write down, and that's all you have to write down. You don't have to show your work. Just write down those two numbers, okay? And then lastly, your ending is, so your ending is this. You've got to make a decision with your p-value, okay? And so we sort of said this in chapter 7, is we would say this p-value, and you write down what it is, 0.002551 is less than less than 0.05. So we're going to compare it to our alpha value, and we'll talk about what the alpha value is, which is a value that is just given to you that if your p-value is below that, you reject the null. Okay, you have evidence against the null. So this p-value is less than 0.05, and if they don't give you an alpha value, you use 0.05. So I reject null hypothesis. Okay, if the p-value was above 0.05, you would not reject it. You failed to reject it, and that's what you would say. So and then you would say, thus we have convincing evidence that, and then you restate the alternative in context. Restate the alternative in context, that the proportion of all gushers in the world that are orange are greater than 0.15. That the proportion of all gushers in the world that are orange is greater than 0.15. So there you go. So in your ending, you're always going to talk about using your p-value to make a decision to reject or fail to reject the null, and do you have convincing evidence for the alternative? In this case, we do, and because we get a low p-value. All right, that's your preview of chapter 9. We're going to go back and work on all this. But thanks for watching the video.